Thank you so much, and thank you all for surviving to the third lecture. It's actually the next room, the most appropriate for this. So just me, or maybe other people? So today the whole talk is going to be really basically around one inequality. So I'm not going to tell you anything broad, but this inequality from a certain point of view is absolutely fundamental. So I'm going to talk about linear extensions of finite posets. And so I'll start with defining posets. So let P x plus be finite posets. So size of x is m, and I'm going to define what linear extensions are. So linear extension f is a map from x into numbers from 1 up to n, which satisfies two properties. One, it's a bijection, okay, and two, it's order preserving, and by that I mean f of x less than f of y for all x and y in x such that x is less than y. Okay, everyone okay with this? That's a very and in fact, if you've been in this room maybe a couple of weeks ago when Robert Tangent gave a talk, he talked about more or less the same thing. Okay, so maybe I can utilize this. So E of P, set of linear extensions of P, and E of P is the number of linear extensions. Okay, that's a notation. Let me give you an example. So suppose this is my poset, and I sort of prefer elements to increase from above to below. Well, I hope everyone is going to be okay with that. So if you're not, let me clarify. So A is less than C, B is less than C and D. Okay, not too hard. And so now I claim that in this case, E of P is 5. So here is how one can see that. So there are sort of 4 easy to find linear extensions. So 1, 2, 4, 3. 2, 1, 2, 1, 4, 3. And there is a tricky one which may not be immediately obvious. So you put 1 here, 2 here, 3 here, and 4 there. Okay, everyone okay with this? I have more examples. So, here is a nice family of examples. So if suppose you have X as a subset, let's say of R plus square, then we can define P corresponding to X as a poset on elements X with the order given by. So if you have so AB is well, let me write the usual. AB is less or equal than A prime B prime if A less or equal to A prime and B less or equal to B prime. So is everything clear? So the poset of this type are called two-dimensional, and that's actually a very large general family of posets. So in particular, let's say, I prepared this example. So if your coordinates go this way, and this is your set X, which happens to coincide with the diagram lambda. So this corresponds to diagram 4431. Then E of P is a number of standard lambda growth of shape lambda, which by the Hookland's formula gives you 2970, whatever. 2970 point is large number. Small set, large numbers. Okay, it shouldn't be that surprising. Everyone okay with this? And before, just to show that this is the reason why we're looking at linear extensions.
Sorry, this comes from the dimension of Hoffman.
Yeah. So this is this is chi lambda of 1. If that helps. Just so we can calculate something rather large. Everyone good?
So what is the definition of SYT?
Oh, that's so SYT is a number of ways. Let me find the nice color. So it's a number of ways literally to create linear extension 1. So which goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Put numbers. This is a combinatorial way to associate numbers from 1 up to 12, which increase in rows and columns, and which happens to be dimension of the reducible rotations of symmetric group corresponding to that diagram. Okay. And so notice that in this case, we could just compute the number by the Hookland's formula. If this was a skew shape, we could have computed it using a determinant formula. But for general legs, that's much less clear. What you do, and of course, this is a theorem that, well, I'll write it this way. Computing the number of linear extension is sharply complete. This is Bragwell and Winkler in the 90, and it's even sharply complete for posets of height 2. Posets of height 2 means that the maximal chain has at most 2 elements, and for posets of dimension 2. Both of these results are by my student Sam Dittmer and myself about 5 years ago.
Dimension 2 that just to explain this.
Say it again?
Dimension 2 means.
Dimension 2 are those which come from here. That's the definition of posets which posets of this type are called dimension 2. In general, one can of course ask, you can put here any D and define dimension to be the smallest D so that the poset can be embedded this way. And there's a whole dimension theory that exists sort of separate from what I'm saying, but posets of dimension 1 are not particularly interesting. Maybe that's an understatement. So the posets of dimension 2 is the smallest one should really think about. And because they contain a lot of posets for which you can compute this, that's a rather interesting class of posets. I should say that
So sharply complete.
everything is sharply complete. Yeah.
Can you remind us what
Sharply complete means?
Yeah.
So it's literally a complete problem in the class Sharpie. So so if you can do so there is a polynomial reduction from number of Hamiltonian cycles, number of three coloring, etc. into this. And however, this problem, number of linear extension, is actually substantially simpler than number of Hamiltonian cycles and or number of three coloring and so forth, because the question whether number of linear extensions is 0 is trivial. It's always at least 1. Okay, so you shouldn't expect a parsimonious reduction. You shouldn't expect to embed a graph into a linear extension which would preserve the number. So this is so the way the proof goes, all using Chinese remainder theorem. So modulo H primes for graphs constructed certain posets, and that allows you to prove that. And moreover, I'll explain why in a minute. Number of linear extensions actually. So this is going to be sort of for people who took a standard graduate class. So has I'll explain what I mean by that. So I'm not going to write parameters. So they do have a polynomial approximation scheme, which means that you can compute it up to 1 plus minus epsilon factor in polynomial time. That may be, you can compute number of linear extensions. That may be surprising a little, but it will become slightly less surprising in a minute. Is everyone clear about the statement?
What does this plus or minus? That's an interval around.
Fully polynomial randomized approximation scheme.
Plus or minus epsilon.
1 plus or minus epsilon. So, so for every epsilon, you can approximate number of linear extension up to epsilon. In time, that's polynomial in n and 1 over epsilon.
Does it mean you can?
Formally, this is 1. Yeah. Say it again.
Does it mean you can both find an upper bound and a lower bound? Yeah.
This is so this R stands for randomized. So this is a probabilistic algorithm. But according to Avi, everything can become deterministic eventually. So you should tell me later how to do that. So I have my doubts. So anyway, so the way so now the next part I'm going to talk about Stanley's inequality. And it's a remarkable inequality. So I'm gonna fix an element in X, and I'm gonna define. And so for every A in from 1 up to n, I'm gonna define n of A. So maybe I should write that n exa. So that's
X is a poset.
so yeah. So I'm going to fix a poset P X less. I'm going to fix an element in X. I'm going to define that to be number of linear extensions of my poset such that f of x equal to A. Okay. And theorem, Stanley, 1980. The theorem is the kind of theorem that you would expect. No, maybe I guess you don't. So this sequence is it's unimodal and even moreover log concave. So for example, what would be the interesting element to take? Let's take this element, then the numbers. So this is x. Let's see. So this is my x. And the numbers that we get is we have let's see, and 2 is 1, and 3 is 2, and 4 is 2. In this example. I hope you can see behind. If you don't, it's pretty clear. And that happens to be log concave, but that's as far as I can do with examples. It's not a particularly obvious what's happening in general. Is this clear? So this was open as a conjecture for a short while, and nobody could even approach. There was no tool to prove that, and I'll tell you basically the proof, the hint of the proof. But now you know where I'm going, right? I'm going to ask about the defect of this inequality. So let's call it a conjecture. Delta A defined as n of a squared minus n of a minus 1, n of a plus 1 is not in Sharpie. I don't know how to do that. Okay. And so let me see. Yeah, I'll tell you. You probably don't want to know the proof, right? So I'll tell you the proof. Why not? So proof sketch of the theorem, not of the conjecture. So what I'm going to do is I'm gonna define other polytope. This is going to be a polytope inside a unit cube. N is still the number of elements in the poset. And the way I'm going to define it is OP is going to be equal to a set of functions g from x to 0, 1, such that g is order preserving. So order preserving, I'm just going to rewrite this very quickly. G of x is less or equal than g of y for all x less than y. Okay, so that's my order polytope. And there was something that Stanley knew, which is from 20 years earlier, essentially that volume of the order polytope is equal to number of linear extensions divided by n factorial. How many people here know this? Okay, quite a few. Maybe. Yeah, sure. Let me just. So let's call it a lemma 1. And so here is a very, very brief proof of lemma 1. So basically, for every f in linear extension, we can define delta f can be defined as a set of g in OP such that g of x. In fact, you can sort of think of that as 0, 1 to the n. G of x is less or equal than g of y for all whenever you have f of x less than f of y. So in the linear extension, you have a complete ordering on the elements, and according to the complete ordering, you're defining that. So this delta happens to be simplex, and then an easy observation: this volume is equal to all the simplexes are the same and very simple. This volume is 1 over n factorial, and that implies the result. Everyone okay with this? Okay. So this is the first ingredient. The second ingredient is more famous, and the second ingredient is called Alexandrov-Fenchelinequality. So theorem, Alexandrov. Let me write that rather quickly. So So it's basically, it was proved in 37 by Alexandrov and not proved in 36 by Fenchel. But otherwise, the attribution is correct. So the way it works is V of, I'll write it Q1, Q2, Q3 dot dot dot. Square is greater or equal than V Q1, Q1, Q3 dot 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 times V Q2, Q2, Q3 dot dot dot. Where V of all Q's is a mixed volume, which is defined, if you like, Q1 dot dot Qn. This is going to be a definition still in want of an explanation. So of volume of lambda 1 Q1 plus dot 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 plus lambda n Qn. So what we're doing is we're taking, and I should have said QIs are convex bodies. QIs are convex in array.
Usually there's a factor in factorial. So
Yes. I don't remember. Where do you think it is? I think it's 1 over n factorial of this.
yes. No,
What?
not that it matters, of course.
Not for inequalities at the end. So so here, so this might look like a definition, but what's hidden here is Minkowski's theory of mixed volumes, that when you take a lambda 1, lambda, etc., lambda n are variables, when you take this volume, that's a polynomial in lambdas. That's not super obvious. And when if it's a polynomial, then you can take a coefficient corresponding to lambda 1 up to lambda n, and that's a number. And that number happens to be non-negative, and that's called mixed volume. Macmillan has a way to explain that it actually is equal to volume of something.
What the connection to the permanent from yesterday? It looks very.
Oh, complete connection. Yeah. So in case where QIs are boxes, the permanent is a mixed volume, more or less by definition. Mixed volume of the matrix is comprised of the length of the boxes. They're all access parallel boxes. So exactly right. That's where it comes from. And so now maybe it's worth pondering what just happened. What just happened is that we know that the volume of the order polytope is what we want. We don't know where this is coming from. Okay, we want an inequality for those numbers, so we need to get them as mixed volumes of something. But first thing is to understand how to get log concavity. So suppose you have just two convex bodies K and L in Rn convex. So we can define, I don't know, Vi to be V of K dot 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 K L dot 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 L, where this number is I. Okay. Then once you write it that way, you conclude that Vi square, that's, I mean, Alexandrov-Fenchelinequality inequality shows that this is equal to Vi plus 1 times Vi minus 1. So you get so you conclude that you actually get log concavity. Do you see what I mean? So by the symmetry, you can sort of concentrate your attention on just the ones two in the middle, either the two Ks or two Ls. That's all that happened. And so now, once you have that, what you do is you modify the order polytope. Let me see. Let me erase something. I'm gonna go. Erase everything here. So now what you do is you define sort of slices of the ordered polytope. So turns I don't know what to call that, OP of X. Well, let me just do the KNL. So let K be the ordered polytope intersected with f of X equal to 0, and L is the ordered polytope intersected with f. Sorry, I think I'm using G. G of X equal to 1. I think that's good enough. Okay, so remember this, my ordered polytope sits in a cube. So I'm just constraining it, and all vertices are going to be vertices of a cube. In fact, vertices are going to be characteristic sets of the upper order ideals. In my posets, so this sort of, so what's going to happen is you divide the posets into two, and you take ones here and zeros here. That's how the vertices are going to look like. So you really are fixing whether you consider X kind of above or below, and then you make an observation that in fact Vi in that notation is 1 over n minus 1 factorial times n of VA is going to be 1 over n minus 1 factorial n of A in this notation, where VI is defined this way. Okay, and that's a little calculation you have to do. Takes one paragraph, and we're done. Once you have that, this constant terms disappear, and you immediately get Stanley's inequality. Okay, absolutely ingenious. And how should I put it? I basically asked Richard, how did you come up with that thing? Because kind of, and he's like, oh, essentially, more or less the same year, van der Waerden conjecture was proved using Alexandrov-Fenchelinequality. And he learned about Alexandrov-Fenchelinequality then, and he tried it all his favorite conjectures, and one worked out. So this is the story. It's not a really complicated story. So maybe pay attention to news, mathematical news, and use what you learn as a moral of this story. Is everyone clear about the proof? I want to move on.
I don't quite understand the intuition behind this Alexandrov-Fenchelinequality.
This is a really hard inequality.
It seems very confusing, right? It's like you take something, mix them in the volumes, and then I take some confusing coefficient of it.
So essentially, it's saying that I don't know. Ramon can tell you later. He understands the philosophy better. But this is a very advanced generalization of the as a geometric inequality, Minkowski inequality, if you understand it correctly, which you would get when you have like one polytope for one convex polynormal, and the rest are all balls. So it's a surprising geometric inequality. It's not. I won't know if I have a really easy way to explain why it's true. I have a long way to explain it, but maybe Ramon later. Don't take my time. Ramon later can tell you a shorter way or more enlightening way to do that, and his name is going to come up soon. But before,
It seems like there's some intuition coming from this proof, actually. As someone that doesn't understand what's on the right board, like what's on the left board kind of makes sense. So I thought maybe there was some way.
So I don't know. So essentially, about 5 years ago or 6 years ago, I wanted to understand that, and this was the only proof that we knew. there are multiple proofs of Alexandrov-Fenchelinequality inequality, but there was no other proof of Stanley's theorem, and I thought that there should be, and in fact, if you maybe this is going to be a sort of step aside, but if instead let me tell you a theorem of Dakin, another Dakin, and Patterson from '84, which says that if you do I'll define it in a minute. So let's denote that to be M of A. So M of A is the value is the order polynomial which is defined as number of I'll use G, number of maps from X to numbers from 1 up to T, such that G of X is equal to A. Do you see what I mean? So
Who is N?
no, T is no. This is gonna be order preserving. Order preserving. Order preserving, but this is not a bijection. So we're not requiring that to be a bijection. And for those of you who know what I'm gonna say, this is more or less Erhard polynomial up to shift in T. Erhard polynomial of the order polyt of OP. And so if we define it that way, then M of A square is greater or equal than M of A minus 1, M of A plus 1, and that's proved by proof via direct combinatorial injection. That's fine. So in this particular case, the defect is on sharp P. We know exactly what it is. So essentially, there is a really nice simple proof, or relatively simple proof of that inequality. Why wouldn't there be a nice simple proof of that inequality? And as a reason,
It's not the same reason that the permanent is hard, but the product of the whole sums is easy. Automatically. Since you don't insist on injection.
so I don't know if it's the same reason, because I really don't know how to formalize what would be the reason here. So I can all I can tell you is what I know, and with my former postdoc Swee Hong Chan, we went on adventure. I'll tell you our result. So let's do a definition. So suppose omega x into R plus, or order reversing. Order reversing is the same thing as order preserving, that's the other way around. So omega of u greater or equal than omega of v for all u less than v. And I'm going to define an omega of A to be the sum over all f in f linear extensions, f of x equal to A of why don't I write product of omega of y for y in x such that f of y less than f of x. So one can sort of think of that as omega of a linear extension. That's the statistics on linear extensions. Okay, it's so omega is a real function. That's the statistics on linear extensions. And if this is too much for you, you can just take omega of x to be always the same number like q, in which case omega of f is going to become q to the size of the downset, not all number of elements that are below x. but anyway, theorem by Swee Hong and myself, and by now you already conditioned to know what's going to come. This is going to be omega of a plus 1 times omega of a minus. Okay, and so when Q is 1, you're gonna get Stanley's theorem. So you know we found another proof of Stanley's theorem. Could be the same proof, you don't know yet. However, what I'm telling you is that if Alexandrov-Fenchelinequality does not give you that. I don't know how to obtain that at all using any geometric means or any other way that we did. So what we used something we call combinatorial atlas, and that's the only proof we have for that.
What did you use?
Combinatorial atlas. It's a complicated linear algebra based technology for proving concavity results. So unfortunately, that paper is about the published version has about 100 pages. It's not something I recommend reading over lunch. But if you want to know what it's about, we have an expository article which gives you introduction to combinatorial atlas, with a title, Introduction to Combinatorial Atlas. Okay, so we do know how to prove that. And the whole reason we wrote those 100 pages is because I thought this conjecture is false. This is my conjecture. So I thought this lecture in Sharpie, and if I get a really sort of basic proof using linear algebra, I would just prove it. I would just construct. I would just prove that there is a combinatorial interpretation. And it took us a while to understand that this is not actually true. That there is no way to approach that. And now I can tell you a stronger result. Is everyone okay with this explanation? Any other questions? Okay. So best way to think about the problem is to look at the actual paper and the actual Stanley theorem, because Stanley actually proves a stronger result. He doesn't single out this inequality. He says the following. So suppose we have p x less. Suppose you have x z1 up to zk. Those are elements. They're all distinct. Otherwise, it's not very interesting. So suppose you have numbers a, c1, .. ck. So those are numbers from 1 up to n, also distinct. I'm going to define n. So z, c, just to make it different, I'm going to define that to be number of linear extensions such that f of x equal to a and f of zi equal to ci. So we generalize. And for the longest time, I thought that this generalization is pointless because this is already very hard. Why do even harder? You probably already figured out what's coming here. Square is greater or equal to n zc a plus 1 times n zc of a minus 1. So you get this strong notion of concavity.
Why did you make this symmetry between x and z?
Because I want a to be the value of f of x, and the values of f of zi are going to be all fixed.
Ah, sorry. Yes.
Okay, so that's why I added parameters here.
But you have in each of those variables,
Of course.
have the same.
Is this clear? And I didn't.
I have nothing with using more than one variable at a time.
The proof is literally the same. He defines the intersection. All you need to do is to put z and c everywhere, and maybe change n-1 to something like n-k or whatever. Okay, so I don't like surprises. So let me tell you the theorem. So suppose k is greater or equal to 2. I'm gonna define delta A in exactly the same way, a squared minus nzc plus 1 times nzc a minus 1. So this is a defect of that inequality. And now I'm going to say that delta A is, or actually, I should have written, well, anyway, delta A is not in sharp P unless pH equal to sigma 2. So, so what we're saying is, so they can Patterson will extend to all these extra variables. However, so that proof just goes by injection, direct injection. I'm saying that in this case, when k is greater or equal to 2, we know it's not going to work. Okay, and that is sort of surprising that we could actually do it at all. And what this is saying, that the Alexandrov-Fenchelinequality inequality, this one, has really complicated equality conditions that cannot be described, and that's actually not in the polynomial hierarchy. So let me write it as a separate result. K greater or equal to 2. Delta, so the question whether delta A is equal to 0. So the question whether we have equality here is not in pH unless pH collapses. And this is a stronger result, of course, than this one. Everything is joined with Swee Hong. Different paper from that one. So then that's because if it wasn't sharp, if this wasn't sharp P, then this problem would be in co-NP and therefore in the polynomial hierarchy. If you didn't follow that sentence, just ignore that. Is everyone clear about this? Yeah, so we're saying that equality conditions for Stanley inequality cannot be described. Okay? Not only you cannot look at poset and bunch of elements and numbers and say there is equality or not. You cannot do that in polynomial time. There is no polynomial witness to that, and much more than that. Do you see what I mean? There is just no way to understand those equality conditions, which in turn is saying something about Alexandrov-Fenchelinequality inequality. I'm not gonna say much about that, but and Ramon would argue that I'm wrong anyway. But it's saying basically that there is no nice stability result for the Alexandrov-Fenchelinequality inequality. For the isoperimetric inequality, for the Brun-Minkowski inequality, there are rather famous stability result. This is saying no, there is no really nice stability result for this inequality if you allow for degenerate polytopes of lower dimensions and n. Okay, so let me.
So sorry, while it's erasing, maybe I can ask. So k greater or equal to 2 means actually that you have to do 3 things.
Correct.
And one thing seemed to be the aim, and two.
But you have to have one thing. One thing is
Yeah.
X.
Yes, but there seems to be like also a middle case where you have k equal to 1.
Yes, we don't know that either. I mean, we do know something, so I may as well tell you. So theorem, delta A equal to 0 is in P when K is equal to 0 and 1. I'm not writing attribution here because it's more complicated. So K equal to 0 case is a remarkable result by Schoenfeld and Ramon, published maybe 23. And K equal to 1 is our result using that technology. And this is really the reason why we couldn't solve this conjecture, because we're not actually proving that theorem, we're proving this theorem. And you cannot extend, and this theorem is tight. You cannot extend it to 0 and 1. Let's see. Okay. So it might be worth saying that, in fact, there is a theorem. So SVH and MS Schoenfeld, which says that delta A is equal to 0. Not only so in fact the decision, so I wrote that the decision problem is in P, but
In which case equals 0, 1, or
well,
in which case are you?
it's so for all K. So let me write it for all K. For all K, delta is equal to 0 if and only if n of a minus 1 equal to n of a equal to n of a plus 1. That in fact the only way you can get log concavity if they're all equal. So when K is equal to 0, so this is SVH and K greater or equal to 1, that's Marshall Schoenfeld. Okay. So this is sort of the first part of the result. The second part, in case K equal to 0, is a complete description of that case. And it also works out when K is equal to 1, but when K is greater than or equal to 2, then this is not enough. You cannot check that easily. And that's the point. Do you see what I mean? And in fact, one of our lemmas, but I'll write it as a theorem. Checking if n of a is equal to, so for K greater or equal to 2, checking whether those the adjacent numbers, unless it collapses, whether adjacent numbers are equal is outside of the polynomial hierarchy.
This requires K greater than 2.
Yes.
Is it false otherwise? I expect this to always be true.
Yeah, me too. But that's all we can prove. And in fact, you know, our proof is a little complicated, but that's what we can do. I think I'm gonna check. I'm gonna have to check later. So
Why K greater or equal to 2 gives you a reduction to this problem. But
yeah.
I expected that this problem itself would always be hard.
give me a second. I didn't actually.
What I just said should not be obvious. It's just
Let me give me 1 second. I'm gonna open. No, that's actually, you're right. You're right. We proved it for full generality, but proved it for k greater or equal to 0. So what, and in fact, yeah, I remember I was looking at that. So the way to think of a graph, what happens is, so this is A, and the graph is, so this is A, and the graph is n of A. So if you have, so what happens, so it turns out that if you, it's easy to check if you have 3 or more on the top.
If k equals 0.
If, oh, I should have said that, sorry, there was one more. So, yes, so now this is the case when k is equal to 0. So checking is strict, so checking if there is one, just one element of 3 elements is really, sorry, if checking if there's 3 or more is really easy. But it's impossible in the polynomial hierarchy to decide if there is 1 or 2 on the top. That's what follows from our results. That's correct. So this is the strangest thing. I'm not sure I have enough philosophy to explain why that happens, other than the fact that this theorem is really a lemma in the proof.
I think it's clear, right? I mean, the Alexandrov-Fenchelinequality is giving you an inequality between 3 things. So we're testing when the inequality saturates, that gives you structure, but there's no inequality between 2 of them. So there's nothing to saturate.
I mean, what we do is, we reduce that to equality for Stanley with 2 more elements. That's how the proof goes. And I don't know if I have more to say about that. So
I'm really sorry. I have
Go
a
ahead.
basic question, if I may. So, what is input here? Is it only the poset or a poset and A? It's only the poset and the
everything. Everything that's written above here, poset, all the elements, all the numbers, that's an input.
A also, okay.
Of course. And you're trying to decide, is this inequality actually inequality? You cannot compute those numbers. That's Sharpie complete. I didn't say that, but just like with the whole number of linear extensions, that's a Sharpie complete. Otherwise, you would be.
This last problem, it's really for fixed A. We are asking this, not whether there exists an A.
No. So, you mean in this picture? Or in what?
There is this last theorem where there is a problem whether 2 things are equal. Is it like A is given or if there is a...
Yes, A is given. A is given.
Okay, thank you.
You're given A, you're given everything. You're trying to decide if those 2 numbers are equal.
Okay.
And when I'm saying no, that's very hard. This is as hard as deciding, and it's not literally true, but it's basically as hard as deciding if two posets have equal number of linear extensions. That's more or less what we embed into here. However, we don't have so in contrast with the result about characters that I was explaining in the first lecture, there is no we don't actually know if this problem is C equal to P complete. We don't know that at all, and it's probably not. We don't know. I'm not sure if one should conjecture that. But we get the result not on the polynomial hierarchy anyway, because we use a somewhat different complexity tools. And I can tell you, let me see. I have about 5 minutes and a couple of pages. Let me let me tell you. What exactly do I want to say? So since I told you about this problem, let me tell you a slightly different problem. So it's a lemma, just like this is really a lemma. Lemma 1. lemma 2 is a lemma of the following type. So suppose you have posets P1, P2, P3, and P4, and elements x1, x2, x3, and x4 in the corresponding posets. So, so the question is whether row P1 x1 times row P2 x2 equal to row P3 x3 row P4 x4. So
What's all?
I haven't told you yet. Where row Px is E of P over E of T minus X. So what we do, so it turns out that this quantity is important. We call it relative number of linear extensions. That's how you would do kind of induction to compute. You see what I mean? And now what we do is a reduction of this problem to that problem, which raises all kinds of questions about what does rho look like and how do you is there any interesting results that you can say about rho? And given that we don't have any more time, let me state a conjecture with which I'm going to conclude.
What was the statement of what one?
So the statement is the same statement as here, that this is not in pH unless pH collapses. In reality, that's not how the statement goes. The statement is that this problem reduces to that problem.
Not
Correct. Yeah, changes a little. So, so let me ask a conjecture. I wanted to finish on a slightly lighter note. This is all kind of heavy. And so here is just an amusing conjecture that comes up from much of our analysis that we do. So I'm going to define E of P as a set of all numbers of linear extensions of height 2, posets of height 2. Okay, that's just a set. So then V, which is integers minus A, is finite. Okay, that looks very reasonable until you try a computer. I mean, this is sort of one of those conjectures where computer tells you one thing and asymptotic tells you another thing. So asymptotically, this got to be true. There is just a huge number of posets of height 2. Even you can sort of look at you can look at bipartite graphs, and there are n over 2 factorial square number of those. And most of them don't have much of a symmetry anyway. So symmetry is small. So there's just a huge number of those. Why wouldn't they have all of those linear extensions is not clear. However, if you start writing that, you realize that P is equal to 7, it starts with 7, 9, 10, 11, 13, 15, 17, it just had 18. It just goes on and on forever. You just can start computing those numbers.
How do you know that?
What?
How do you know, for example, that 7 is in B?
Oh, you just try.
But you don't know. I mean, there could be some possible.
Oh, it's very easy to get a lower bound so as the size grows, the number of linear extensions of poset of height 2 has to be large enough.
So just for any finite number.
Yeah, for any finite number, you can compute it in finite time. Exponential, but still finite. So this is eventually it becomes higher. I computed this by hand. This is not actually, you don't need a computer for that. So I asked, so I had a PhD student who just finished David Sukop, who proved the theorem. And this is going to be the very last thing I'm going to write. 1593350. The numbers are very important. 922 239999. That's in B. So I mean, his theorem is more complicated. But basically, this is the largest number that we can compute. That's actually, we can show that it's not an A.
Using computer.
Yes. I mean, without computer, I don't know how to even, I barely can write it. This is like 1 quintillion something. I mean, but it's basically computer is used as a calculator, not anything else. He's not doing any searches. So just to be clear, if you add 1, that's in A. So this is like the largest number for which he can actually prove. And this sort of suggests that this conjecture might be false, but I stand by my conjecture. So I think it's still true, and I think it's very interesting. And I challenge you to do that. So thank you all.
Question?
What happens if you do 3 instead of 2, right?
3 what?
Height of the poset.
Oh, yeah, I don't know, but in fact, random, so you might like that. Random posets have height 3
What is a random?
with uniform.
Of a fixed size n.
A fixed size n. You know, if you pick a true with high probability, that's going to be of height 3.
For n.
Yeah, and in fact, this is one of so pleased to say that this is a theorem by Danny Kleitman and Bruce Rothschild, who is at UCLA. So those are sizes n over 4, and the middle size is n over 2. That's what random posets look like. This is a theorem from, I want to say, late 60s. But we don't know that either. So we do know stuff. Let me not tell you. I know a lot of stuff about what happens. So we do know it if instead of height 2, put width 2. Then we know that, and we know much more. We know that it can be a logarithmic size. More or less.
So then it's infinite.
No, so for other classes of posets, we know this is true. And something even stronger is true, but we don't know for height 2. And that's because essentially the numbers grow very rapidly.
You know it's infinite for some.
A is infinite, yes.
No, I mean B is infinite for something.
No. For other classes, well, yeah, if they're width 1, yes. There is really not much to say. But for natural classes, no. So part of the reason we needed to analyze this the number theory that comes up here, because it comes up in the proof, and it comes up in the proof of the main theorem, wherever in the proof of that theory. This is sort of like stuff related to the lemma that goes in the proof of that result. I just really wanted to write that number.
Is it pi?
No, but it's something really nice, like a factorial of something, like 20 factorial square minus 1. It's that kind of number.
Because A is multiplicative, right?
Yes. No, actually, no. A is not multiplicative. So when you put two posets, next to each other, you multiply by a binomial coefficient. So you have to increase the height to make it multiplicative. And then close to multiplicative, but not exact. But I checked.
Can you just make one poset on the top and then on the bottom? No.
Height two.
Oh, height two, right.
That's the point. I checked, and A modulo some conjectures, A contains infinitely many primes. So that's not really much to go for. But it does have a lot of primes in it, so don't try to. This comes from very beautiful. So one can consider a generalization of the poset I started with that corresponds to alternating permutation. And number of alternating permutations given by Bernoulli numbers, and Bernoulli numbers have a lot of prime factors. And there's more to the story, but that's a well-known in both in combinatorics and number theory. That's a well-known stuff. So just those posets already give you quite rich family of numbers, sequence of numbers.
What's the next largest number, the previous largest number before this one that you wrote out? Did the gaps increase?
The previous one?
Yes.
Same thing with 98.
So.
Yeah, there was like an interval. There was a large interval, well, large as in, I mean, it's small compared to the number, but large compared to like number of people in this room. I forgot what is the length, but it's several thousand.
Oh.
Yeah, so but it's the last largest interval. It's the last interval we can prove exists. It's like, because at some point asymptotics just catch up with it. So we don't, so that's all we know. So the largest number we know that's not an A. Okay, thank you all.